Download this code from codegive.com, link in the description below. The 8086/80186 nested bug scenario, a deep dive. The term 82116 nested bug isn't a standard classification. The 8086/80186 family of processors didn't have a single, well-known bug specifically called nested. However, the architecture's limitations and potential for interaction between interrupts, exceptions, and software bugs can lead to complex, nested failure scenarios that mimic the concept. This tutorial will explore such scenarios, focusing on how bugs can interact and lead to seemingly unpredictable behavior within the same thread. Understanding the foundation, interrupts and exceptions. Before delving into nested bug scenarios, we need to understand interrupts and exceptions on 8086/80186 processors. These are mechanisms that interrupt the normal flow of execution. Interrupts triggered by external events, example a hardware timer, keyboard press. They use the interrupt vector table to jump to a specific interrupt handler routine. Exceptions triggered by internal events, example division by 0, invalid opcode. They also use the interrupt vector table but represent error conditions. The potential for nested bugs. Nested bugs arise when a bug in one part of the code, example within an interrupt handler, triggers another bug in another part, example in the main program or a different interrupt handler. This creates a chain reaction that can be difficult to debug. Let's consider several scenarios. Scenario 1, Stack corruption and interrupt overlap. Consider a scenario where a bug in the main program corrupts the stack. This corruption might not immediately cause a crash, but it could lead to unpredictable behavior. Then, an interrupt occurs, example a timer interrupt. The interrupt handler pushes data onto the stack. Because the stack is already corrupted, the interrupt handler might overwrite critical data or fail to save the necessary registers, leading to a crash or unpredictable behavior upon return from the interrupt. Code example, illustrative, assembly. Scenario 2, unhandled exceptions within interrupt handlers. An interrupt handler might contain its own bugs. For instance, it could perform an operation that leads to an exception, example division by 0. If this exception isn't properly handled within the interrupt handler, it might lack appropriate error checking. It could cause a system crash or unpredictable behavior. This is a nested bug because the initial interrupt's execution triggers another, independent failure. Scenario 3, recursive interrupt calls. Though rare in well-designed systems, poorly written interrupt handlers could inadvertently trigger another interrupt. This could create a recursive chain of interrupts leading to stack overflow and system crash. This is particularly dangerous with interrupts that are maskable, can be temporarily disabled. If the interrupt handler doesn't re-enable interrupts correctly, it could block all further interrupts, leading to a system freeze. Debugging nested bugs on 8086/80186. Debugging these kinds of nested failures is challenging. Here are some strategies. Careful code review. Thorough code reviews, especially for interrupt handlers, are crucial. Pay close attention to stack management, error handling, and interrupt masking. Simulators/debuggers. Use debuggers that allow single stepping through code and inspecting registers and memory. Simulators allow controlled environments for recreating and analyzing the bug. Logging/tracing. Insert logging statements to track the flow of execution, especially across interrupt handlers. This can help identify the sequence of events leading to the failure. Memory dump analysis. After a crash, Analyze a memory dump to identify corrupted memory regions or unusual stack contents. This can pinpoint the root cause of the initial bug. Interrupt disabling. With caution, temporarily disabling interrupts can help isolate the problem by preventing interruption interference. However, this should be done carefully and temporarily because it may mask other issues. Modern equivalents. While the 8086/80186 architecture is obsolete, the concepts of nested bugs remain relevant. Modern processors and operating systems have sophisticated interrupt and exception handling mechanisms. However, poorly written code can still lead to similar complex failure scenarios involving interacting bugs across different parts of the code, threads, and interrupt handlers. The key principles of careful code design, robust error handling, and thorough testing remain crucial for preventing and debugging these types of issues regardless of the underlying architecture. This tutorial provides a conceptual overview and illustrative code examples. Real-world debugging of such nested bugs requires extensive experience and the use of sophisticated debugging tools. Remember that the exact nature of a nested bug depends heavily on the specific code and circumstances. The scenarios presented highlight potential failure modes and the importance of defensive programming principles.